Imagine standing at the edge of a great ocean. The water stretches out, a vast and mysterious world just beneath the surface. For a few frantic moments, a human can hold their breath and dip below, entering this silent blue kingdom. But it is only ever a brief visit. We are creatures of the land, bound to the air. No matter our courage or our desire, a hard boundary exists. We can swim, we can dive, but we cannot stay. The water, which gives life to so much of our planet, will ultimately take ours if we linger too long. It is a profound and unyielding truth of our biology. This boundary raises a simple yet deeply compelling question. Why? Why can we not breathe where countless other creatures thrive? The answer is not as simple as it may seem. It is a story written over millions of years, a tale of evolutionary choices and the intricate machinery of life itself. It guides us back through our own history, revealing the very essence of what makes us human. By understanding this limitation, we begin to understand the remarkable journey that led us to stand on 2 feet, looking out at a world we can see and touch, but never fully inhabit. It is a journey into the mechanics of breathing and the separate paths life has taken. In this exploration, we will look at the fundamental differences between our world and the world beneath the waves. We will discover that the problem is not a lack of life-giving oxygen in the water, but rather our method for collecting it. We will journey into the delicate feathery architecture of a fish's gills and contrast it with the spongy, air-filled sacs of our own lungs. We will see how 2 different solutions to the same problem, the problem of staying alive, have created 2 entirely distinct forms of existence. One is not better than the other. They are simply different paths, each perfectly suited to its own environment. The story of why we cannot breathe underwater is, in the end, the story of who we are. It speaks to the incredible pressures that shaped our ancestors, forcing them onto land and setting them on a course that would eventually lead to us. It is a tale of trade-offs and specializations, of opportunities gained and abilities lost. By peeling back the layers of this biological puzzle, we uncover a deeper appreciation for the intricate and often invisible forces that have sculpted all life on Earth, including our own. It is a reminder that we are one branch on a vast and ancient tree of life. It is a common misunderstanding to think that water contains no air for us to breathe. But that is not quite right. Water is, in fact, saturated with dissolved oxygen. Every river, lake and ocean teems with this essential gas. It is the very same oxygen that fills our atmosphere and sustains us with every breath we take. The fish, the crabs, the countless invertebrates that call the water home are all breathing this oxygen. The challenge, therefore, is not about the absence of oxygen, but about the difficulty of its extraction. The air is simply in a different form, woven between the molecules of water itself. Imagine oxygen as tiny, invisible bubbles scattered throughout a vast container. In the air, these bubbles are plentiful and easy to gather. We simply open our mouths and draw them in. But in water, these bubbles are far more spread out, and they are suspended within a much denser substance. A lungful of air contains about 20 times more oxygen than the same volume of water. This means that any creature living underwater must work significantly harder and be far more efficient to gather the same amount of life-sustaining gas. It is a world of scarcity, requiring a unique and specialized tool. This fundamental difference is the starting point of our story. Life in the water had to solve this problem of extraction with incredible efficiency. It needed a system that could process enormous volumes of water, filtering out the precious few molecules of oxygen suspended within it. The evolutionary path of aquatic life was defined by this challenge. The solution they arrived at is one of nature's most elegant and effective inventions: the gill. It is a structure born from the necessity of pulling life from a world where oxygen is sparse and difficult to access, a world so different from our own. So, when we look at the shimmering surface of a pond, we should not see it as a barrier separating a world with air from one without. Instead, we should see it as a boundary between two different states of oxygen. Above, it is abundant and free. Below, it is scarce and dissolved. Understanding this distinction is the key to unlocking the entire mystery. The story is not about what is in the water, but about the biological machinery required to get it out. And the machinery of a fish is a world away from our own. To understand why we are bound to the land, we must first look closely at the creature that has mastered the water. We must look at the fish. The secret to its aquatic life lies in a remarkable piece of biological engineering: the gills. These are not simple filters, but complex living organs, perfectly tuned to their environment. Located on either side of a fish's head, often protected by a bony plate called the operculum, the gills are the fish's equivalent of our lungs. They are the gateway through which the outside world enters the body, bringing the vital gift of oxygen. When we look inside, we see an intricate and beautiful structure. Each gill is composed of several gill arches, bony or cartilaginous supports that act like a scaffold. From these arches, rows of delicate thread-like structures called gill filaments extend outwards like the teeth of a comb. If you were to look even closer at these filaments, you would find that they're covered in even smaller microscopic folds known as lamellae. This intricate layered design is no accident. It is a strategy to create an enormous surface area packed into a very small space. This vast surface area is the first part of the gill's genius. If you were to unfold all the lamellae from the gills of a single fish, they would cover a surprisingly large area. This is essential because it maximizes the contact between the fish's blood and the surrounding water. More contact means more opportunity for oxygen to pass from the water into the bloodstream. It is a simple principle of efficiency, taken to an evolutionary extreme. The gill is, in essence, a living net with a microscopically fine mesh designed to catch as many oxygen molecules as possible as water flows past. The reason for this complexity is simple. Water, as we have learned, holds very little oxygen compared to air. To survive, a fish must be incredibly efficient at capturing what little is available. It cannot afford to let any opportunity slip by. The gills are a direct response to this environmental pressure. Their delicate feathery form is a testament to millions of years of refinement, a perfect solution to the challenge of breathing in a dense and oxygen-poor medium. They are a true masterpiece of natural design, enabling life to flourish in a world we can only visit. The function of the gills is a continuous and graceful process, an intricate dance of water and blood. A fish breathes by constantly drawing water into its mouth. Instead of swallowing this water, it forces it to flow over the gill filaments and then out through the gill slits. This creates a steady, one-way current. It is a far more active process than our own passive breathing. The fish is continuously pumping its environment through its respiratory system, actively seeking out the oxygen it needs to survive. This constant flow is crucial for ensuring that fresh, oxygen-rich water is always in contact with the gill surfaces. The true marvel of the system, however, happens at the microscopic level of the lamellae. Here, blood flows through tiny capillaries in the opposite direction to the water flowing outside. This mechanism is known as countercurrent exchange, and it is the secret to the gill's incredible efficiency. As blood that is low in oxygen enters the gill, it first meets water that has already had most of its oxygen removed. But even this used water still has more oxygen than the deoxygenated blood, so diffusion occurs. The blood picks up some oxygen. As this same blood continues to move along the lamella, it encounters water that is progressively richer in oxygen. By the time the blood is ready to leave the gill, it is meeting the freshest, most oxygen-rich water that has just entered. This ensures that the concentration gradient, the difference in oxygen levels between the water and the blood, is maintained across the entire length of the gill. The blood is always next to water that has a slightly higher oxygen concentration, allowing it to continue absorbing oxygen until the very last moment. It is a system of remarkable subtlety and power. Thanks to this countercurrent exchange, fish gills can extract over 80% of the dissolved oxygen from the water that passes over them. This is an astonishing level of efficiency, born from the necessity of surviving in an oxygen-scarce environment. It allows a fish to thrive where we would perish in minutes. The gill is not just a filter. It is a highly sophisticated exchange system, honed by evolution to perform a difficult task with unparalleled grace. It is the key that unlocks the aquatic world, a key that our own biology simply does not possess. Now, let us turn our attention inward to our own bodies. Our tools for breathing, our lungs, are just as specialized as a fish's gills, but they are designed for an entirely different world, the world of air. Our lungs are not delicate external filaments, but two large, spongy organs housed safely inside our rib cage. They are not designed for a constant flow of fluid, but for the gentle ebb and flow of gas. We breathe in, filling them with air, and we breathe out, expelling what is left. This tidal, two-way system is perfectly suited for an environment where oxygen is abundant. When we inhale, air travels down our windpipe and into a branching network of smaller and smaller tubes, known as bronchi and bronchioles. This structure is often called the bronchial tree, and it resembles an upside-down tree, with the trunk at our throat and the tiniest branches deep within our chest. At the very end of these branches are microscopic air sacs called alveoli. We have hundreds of millions of these tiny balloon-like structures in our lungs. It is here, in the quiet darkness of our chest, that the magic of our breathing happens. Just like the lamellae in a fish's gill, the alveoli are all about maximizing surface area. If you could flatten out all the alveoli in an adult's lungs, they would cover the area of a tennis court. This enormous surface is lined with a vast network of tiny blood capillaries, just a single cell thick. When air fills the alveoli, oxygen effortlessly dissolves into a thin layer of moisture and then passes across the thin walls of both the alveoli and the capillaries, directly into our bloodstream. Carbon dioxide, the waste product of our metabolism, makes the same journey in reverse. This system is elegantly simple and incredibly effective in air. Because air is light and oxygen is plentiful, we do not need a one-way, high-efficiency system like a fish. Our tidal breathing, which leaves a fair amount of stale air in our lungs after each breath, is more than sufficient. We can afford to be less efficient because our environment is so rich in what we need. Our lungs are a product of life on land, a perfect adaptation for a world awash with oxygen. They are a testament to the evolutionary path our ancestors took when they left the water behind. So, what happens when this system, so perfectly designed for air, encounters water? The result is catastrophic for several reasons. The first and most immediate problem is the sheer physical effort required. Water is nearly 800 times denser than air and about 50 times more viscous or thicker. Trying to move this heavy, syrupy fluid in and out of our lungs' delicate branching structure would require an immense amount of energy. Our diaphragm and chest muscles are simply not strong enough to perform this task for more than a few breaths, if at all. We would quickly exhaust ourselves just trying to breathe. Even if we could somehow manage the physical effort, the structure of our lungs would fail us. Unlike the rigid, supported filaments of a gill, our millions of tiny alveoli are delicate, balloon-like sacs. They stay open in air because of the surface tension of the thin fluid that lines them and the pressure of the air within. When filled with water, however, these delicate structures would collapse under the fluid's weight and its cohesive properties. They would stick together like wet plastic bags, unable to reinflate. The vast surface area so crucial for gas exchange would be lost instantly. Furthermore, the process of gas exchange itself would grind to a halt. Our lungs work by allowing oxygen to diffuse across a very thin, moist membrane. This system is calibrated for the high concentration of oxygen found in the air. Water, as we know, contains far less oxygen. Even if our alveoli did not collapse, the amount of oxygen we could extract from water using our inefficient tidal breathing system would be nowhere near enough to sustain us. We would be starving for oxygen even while completely submerged in a fluid that contains it. This is the grim reality of drowning. It is not simply the filling of the lungs with water, but the complete and utter failure of a biological system in an environment for which it was not designed. The lungs are flooded, the alveoli collapse, and gas exchange ceases. The brain and other vital organs are starved of the oxygen they need to function. It is a swift and irreversible process, a stark demonstration of the hard boundary that separates our world from the world beneath the water. Our lungs, our lifelines in the air, become our anchors in the deep. Beyond the mechanical differences in gills and lungs, there is another, more fundamental reason why humans could never breathe underwater. It lies in the very nature of our metabolism. Mammals, and humans in particular, are warm-blooded or endothermic. This means we generate our own body heat, maintaining a constant internal temperature of around 37 degrees Celsius, regardless of the temperature outside. This ability allows us to live in a wide range of climates, from the frozen Arctic to the scorching desert. But this incredible advantage comes at a tremendous cost. Maintaining a constant internal temperature is an enormously energy-intensive process. Our bodies are like furnaces, constantly burning fuel, the food we eat, to generate heat. This metabolic fire requires a vast and continuous supply of oxygen to keep it going. Compared to a cold-blooded or ectothermic fish of the same size, a human has a metabolic rate that is roughly 10 times higher. We live our lives at a much faster, more energy-hungry pace. Our demand for oxygen is simply insatiable. We need more fuel, and we need to burn it more quickly. This is why we need lungs in the first place. Only by breathing air, with its high concentration of oxygen, can we possibly fuel our high-speed metabolism. The slow, difficult process of extracting oxygen from water, even with the most efficient gills, could never supply the amount of oxygen our warm-blooded bodies demand. A human-sized creature with gills would be in a constant state of suffocation. It could not generate enough heat to stay warm, nor could it power a large, complex brain, the most oxygen-hungry organ of all. Therefore, even if we were to imagine a hypothetical human with perfectly functioning gills, our biology would still fail us. Our entire physiology, from our warm skin to our thinking minds, is built upon the foundation of a high-energy metabolism fueled by the abundant oxygen in the air. The evolutionary choice to become warm-blooded was also the choice to forever abandon the water. We traded the efficiency of the gill for the power of the lung, and in doing so we committed ourselves completely to a life on land. The fire within us is too bright to be sustained by the water. It can be tempting to view our inability to breathe underwater as a kind of failure, a limitation or a weakness in our design. We look at the fish gliding effortlessly through its liquid world, and we may feel a sense of envy for a freedom we do not possess. But this perspective misses the profound truth of evolution. Our adaptations are not failures, they are specializations. We did not lose the ability to breathe water. Rather, our ancestors traded it for a suite of powerful new abilities that allowed them to conquer a different realm. The land. The move from water to land was one of the most significant events in the history of life. It required a complete re-engineering of the body. Gills were replaced by lungs. Fins slowly transformed into legs. Skin had to adapt to prevent drying out. This transition was not made because life on land was inherently better, but because it presented a new set of opportunities. The ancestors of all terrestrial vertebrates, including ourselves, embarked on this journey and in doing so committed to a new way of life. They specialized. Our lungs, our warm-blooded metabolism and our large brains are all part of this terrestrial package. They are features that allowed us to thrive in an environment rich with oxygen but fraught with new dangers like gravity and dehydration. Our ability to run, to climb, and to think in complex ways are all downstream consequences of this ancient transition. We are creatures of the air, and our entire biology reflects this fact. To wish for gills is to wish away the very adaptations that make us who we are. It is like a bird wishing it could swim like a penguin, forgetting that its wings give it the freedom of the sky. Therefore, our boundary with the water is not a wall that holds us back. It is a line that defines us. It is the result of a journey that began hundreds of millions of years ago. A journey that prioritized a high-energy, active existence on land. We traded the slow, patient world of the water for the fast-paced, dynamic world of the air. This was not a failure to adapt to the water, but a spectacular success in adapting to the land. Our limitations are simply the other side of our strengths. So we return to the water's edge, with a deeper understanding of the invisible boundary that lies upon its surface. We now know that it is not a lack of will, but a matter of machinery, metabolism and history that keeps us here on the shore. Our lungs are tuned to the air, our bodies burn too hot for the water's limited oxygen, and our evolutionary path diverged from that of the fish an unimaginably long time ago. We are, in every fibre of our being, creatures of the land. This truth does not diminish the wonder of the ocean. It enhances it. It allows us to see the world beneath the waves not as a place we are barred from, but as a testament to a different way of being. The fish, with its elegant gills and its patient, cold-blooded existence, represents another possible answer to the question of how to live. It is a parallel world, governed by different rules and solved with different biological tools. Our inability to join it reminds us that evolution is not a ladder leading to a single perfect form, but a branching tree, with each branch finding its own unique way to thrive. To be human is to carry the history of our terrestrial journey within us. It is to have lungs that remember the richness of the air, and a metabolism that recalls the need to stay warm in a changing world. Our limitations are a part of our identity. They connect us to the land we walk upon and to the air we breathe. They remind us that we are not universal beings, capable of anything, but specialized creatures, exquisitely adapted to one particular and beautiful corner of the universe. And so we stand here, not as prisoners of the land, but as its children. We can look out at the vast, mysterious ocean and feel a sense of connection, not through shared biology, but through a shared origin on this one life-giving planet. We can appreciate the profound beauty of the path we have walked, a path that led us out of the water and into the air, gave us hands to build and minds to wonder, and ultimately allowed us to stand here and simply ask the question, why? That in itself is a remarkable destination. If you enjoyed this journey, subscribe for more fascinating science stories.